All right, so we've talked about electric field, and the idea of voltage is tied really tightly to electric field. And so now we'll see if we can get the flip side of that pairing and talk about voltage. All right, so we're going to start. I keep talking about hills and boulders. We're going to talk about boulders here. So if you remember from 151 or earlier physics classes, the work energy principle says that the net work is equal to the change in kinetic energy. Fairly straightforward, right? You do work on an object, you're adding energy to that object, and it's going to start moving. Okay, but if I lift a boulder above my head and there's no friction involved, uh, and it's motionless both before and after, how can this equation be true in that situation, right? I've done a bunch of work to it. Why haven't I increased its kinetic energy? And this is a picture of me in my salad days there. I did a lot of boulder lifting back in my days. So let's see if we can figure that out. Why haven't I added kinetic energy to this boulder? So the net work on the rock is going to be the work that I applied to it, but it's also going to be the work that gravity is doing on it. So gravity is working on it because it's moving while there's a force being applied. So we'll figure out what that work is. So my applied force is F times D times cosine theta. And if you remember, that theta is just the angle between these two vectors. Same with gravity. The difference is that this, for my applied force, is both the force and the direction of movement, D, are straight up. So my cosine is of 0, and that's equal to 1. This one is cosine of 180 because gravity is pulling down as the rock is going up. So that's a negative 1 term. And so my equation ends up being this when I've inserted those cosine values. The applied work minus the work of gravity is equal to 0. So gravity is doing negative work here. And that means that the total work on the boulder is 0. Okay, there's no kinetic energy here because my net work, in fact, is 0. I've done some applied work, but gravity has done some negative work. Where does my work go? Well, it goes into potential energy, right? So since gravity is a conservative force, when work is done, a negative work is done by a conservative force, that turns into potential energy. When I lift that boulder up, I'm working against gravity, and it is stored as gravitational potential energy. So the boulder hasn't gained any kinetic energy, but it has gained potential energy, which then I can, convert back to kinetic energy should I need to by dropping a boulder on my enemy. I did that a lot back in the day too. A lot of boulder dropping. All right, so why are we talking about boulders? We're talking about hills and maps. Now we're talking about boulders. What are we doing? Well, we want to talk about potential electrostatic energy. Electrostatic force, like gravitational force, is conservative. And so if I take this point positive Q and I push it leftward towards this positive plate, I'm effectively pushing it uphill, right? Electrostatic force wants it to go right, but I'm going to push it left, just like I lifted that boulder while gravity wanted it to go down. What I'm doing is I'm storing energy in that charged particle by doing work on it. So I'm pushing it over here. What happens when I let go of it here? Well, it flies over to the right, right? So that's just like lifting that boulder into the air. The potential energy that I added with my work turns into kinetic energy. In a situation like this, we can talk about a difference in potential at two different places. For gravity, this is really just a matter of elevation, right? I can have point A and point B, and this is important to remember. When we talk about difference in potential, we're talking about two different places, okay? So at point A, I'm at 0 meters. At point B, I'm at 10 meters. This is a potential gravitational difference of G times H, and you recognize gravitational potential energy is m times g times h. So we're really just dividing that by mass, by kilograms, and we get something in the units of joules per kilogram. So for every kilogram I move from point A to point B, I'm going to add 98 joules of potential energy. Okay, if I move a 1 kilogram rock, it's going to give me 98 joules. If I move a 10 kilogram rock, it's going to give me 980 joules. That's a potential difference in terms of gravity. When we talk about potential difference for electric fields, we call it voltage. And remember, just like in voltage, it's two different places. It's like this bar over here, which is positively charged, this bar over here, which is negatively. These are going to have two different voltage, like two different elevations. And that voltage is going to be in units of joules per coulomb. That is energy per unit charge. Just like for elevation, it was joules per kilogram. Here it's joules per coulomb, or volts. And that's what we'll call them from here on out. And voltage is not an energy any more than that G delta H is energy. Voltage is more like point A at 0 meters and point B at 10 meters. If I move a bunch of charge from 0 volts to 10 volts, then I'll have a bunch of stored energy, okay? But the voltage just describes those two different places, those two different elevations. So a boulder that is 10 meters above the ground has a lot more potential energy than a pebble 10 meters above the ground, right? If I lift a boulder above my head, that's got a bunch of potential energy. If I lift a pebble, not so much potential energy. But they have the same potential difference, okay? If we think about that in terms of like a car battery and a handheld battery, right? They might both be 12 volts. But in a car battery, I've moved a whole bunch of electrons and stored a whole bunch of electrons at a higher voltage. And in a handheld battery, I've moved much fewer, okay? So it's got the same voltage, but a different amount of stored energy. We can also look at it in terms of this image over here. Let's say I have 10 volts over here and 0 volts over here. If I push a really big charge, you know, Q equals, I don't know, 10 coulombs or something, and I push it all the way over here, I'm going to store a bunch of charge, okay? But if I just push a tenth of a coulomb charge across that voltage difference, I'm going to have less energy, just like lifting the pebble up compared to the boulder. Okay, so voltage describes two places that if I move charge, it's going to require work and it's going to store potential energy, but it's not energy itself. Now we can see why equipotential lines are called equipotential lines. They have an equal potential, okay? So they are like elevations. Those are the topographic lines on our map. This line is negative 10 volts. This line is negative 5 volts. This line is negative 2 volts, right? Or on a flat plate like this, they're going to be nicely divided, 75 volts, 50 volts, 25. This is like moving up the hill, right? If I take my boulder and I move it 5 meters up the hill, I move it 10 meters up the hill, I move it 20 meters up the hill, it's going to have a lot of energy when it falls down. If I take my pebble, it's going to have a little bit at 25, a little bit more at 50, and still a little more at 75, but much less energy than when I moved my boulder that far. And another parallel with gravitational potential energy, it's difference that matters. Remember, with gravitational potential energy, we can set y equals 0 wherever we want. We can do the same thing with voltage or with electric potential. Okay. Usually we designate what's called ground as 0 volts. That is, we've connected something to the earth, which is largely uncharged, and we call that 0. But we don't have to call it 0. It doesn't matter. It's just going to make our calculations easier if we call it 0. So 0 volt, we could call this, 0 and that negative 100, and it would serve the same purpose.